Part 2 of how to get into the Minut M2 IoT device. Quick recap. This is an IoT device that will often be used in short-term rentals to keep track of guests. Are they doing too much noise? Are there too many of them? You can also use them at home. They recognize breaking of glass and stuff like that. I've had them for a while. Last episode, we ended on being able to read out the boot binary from the RAM. And now we're going to go into Ghidra. And here we are. I've loaded up a fresh binary that I've just run analysis on to get the ARM instruction decoding. And we're now going to start to take a look. Now, a great way to start looking through a binary like this is to remember that when we did strings, we actually found stuff. So let's do strings again, and now here in Ghidra. Actually, I mean, we know sort of what we want to find. So vol is where the keys were. And then we're gonna check and see, here's the help for the command vault. So we click on that. And then go and see where that's used from. This function that's now being decompiled by Ghidra likely has to do with vault. I mean, it's a great assumption to have. And the trick now, because of how you address stuff effectively in ARM, is to scroll down until the end of this function. And here's a list of pointers. I mean, I can see this is within the SRAM memory range. If we do that, they're going to get dereferenced by Ghidra, and it's going to change. And you can see that already here. You can see that in the code, it now says pointer to a string, failed to create a vault iterator. So by doing this, we're going to find something magical. Here, it prints something about usage. It apparently can fail to create a vault iterator. It will print how much space we have left. We saw that. Here you can do add of a type. There's an illegal type. It's not permitted to add a key. Apparently keys are supplied as base64 data. Add object failed, add file, illegal type, could not read file, could not open file, add object. Okay, so here's the vault command. It clearly is. That's the one we were running before when we were using the serial interface. So command vault. And now my idea was, of course, that this is a command that lists the different keys or the names of the keys, etc. So hopefully somewhere in this code, it's going to read the keys from the vault up into RAM. And, you know, we can dump RAM. And that would be a game over. We would have all the keys. Now, a thing with STM32 and ARM is that you're able to address the whole memory range, including peripherals and internal flash, everything, as memory addresses. So while all of this you can see is in this range, which is the SRAM, you could just start addressing things outside of that range. And if we're lucky, we're going to see something else. I'm just scrolling down here. And here's one such reference. As you can see, this is a pointer to a different memory range. And this, 08, is actually the memory range of the internal flash. And I happen to know that 802 is where application firmware will reside, the application, once it's been decrypted. 0 here would be where the actual boot is. They boot off the internal flash. And so by knowing this, that this is how it's addressed, if that's how they access the keys, we're not going to get them into our nice little exploitable RAM. So we need to do something else. Now, if you type boot in the serial console, the application will start. And when it does that, it says something about secboot, it says verifying application, etc. And it's reasonable to assume that it's doing decryption there. So if we go to secboot, verify application, there we go. We go to this method, we do the same trick again so that we are finding out. And here we have that address, by the way. Flash driver error, sec boot, failed to boot, verifying application. Well, this is a reasonable assumption that we're talking about what we just saw, the code that verifies whether you're allowed to start up an application. And so we're going to rename this as sec boot, and then we're going to look through. Okay, flash driver error. That tells me that this is likely where it's loading the file from the internal flash and then checks to see whether it's valid. That works. It's going to do verifying application, and then we have a method call, and then we have a method call that returns something, and depending on that value, it's going to either do this function and then something else, and those two are the same regardless of that value. It's a good guess that it's checking here whether we're allowed to start it. If so, this method is likely going to relinquish control. Disable interrupts, set main stack pointer, set process stack pointer. Yeah, there we are. So now we know that this method checks whether the application is valid. So let's scroll down. And I have done that before, so I do recognize some of this. The key access is going to be in here. Then we have a loop where it's doing some sort of operation, depending on whether that operation over some sort of length or 32 bytes. We're going to progress here. And I've gone through this. I realized after having decompiled this method and a lot of other methods that to get any further, I needed to have this code being run. Just doing the secboot thing is not enough because I am not able to change the code that is coming from the internal flash. I need to be able to run the code that verifies the application firmware and the boot firmware files as they are loaded onto the internal flash from the external flash. Now, I mean, if you need firmware for an IoT device, that's simple, right? You just go to the manufacturer's website. So let's see if we can figure out on the Minut website how to download the firmware. Do you have a feature request? Boot your Minut's firmware are updated regularly. Sensor swap. Okay, well, that sounds good. Locate sensor swap in the app. Well, all of this just says that I need to do that from the devices. Is there any way to get new firmware onto device? Let's see, recovery maybe? No articles for recovery. What? Download then. It turns out that there's actually no way to download the firmware for the Minut devices. It's not available. At this point, I went to search engines. Now I can't show you this because I'm actually unable to get those results back. They have been scrubbed. But searching using search engines, I was able to find a link to part of Minut's website that talked about some sort of a PC recovery tool. And thankfully, it was still possible to download the app image of that recovery tool. Now I ran it, as you can see. Unfortunately, it didn't work. Now I started out by trapping inside the binary because I wanted it to download the firmware and then halt. I didn't want it to try to upgrade my device, which I needed to connect. But nothing happened. It wasn't downloading. And at this point, I tried figuring out, was it my VPN? Was it running this in Kali? What was the problem? And after a while, I actually gave up. Now, I'm an owner of these devices, I subscribe to the cloud service, I jumped on the site, and I asked customer service. I'm unable to run the P2 recovery, the update utility. Can you help? Is it a server thing? And they thanked me for telling them that this page was still available and that this tool was unsupported and that I couldn't use it. Now, I tried my best. I really tried the nice, friendly social engineering path here. I talked about how I had several devices. I was such a happy customer. And I really just wanted to get one of the devices that just couldn't start up. I just wanted to recover it, just as the tool was designed to do. No help. These devices are out of warranty. Okay. However, I still had the app image. And so here is the URL that I built up that still, if you run it, it's going to return another URL through JSON, which has some sort of UUID in it. And that URL, if we access it, is going to get us the web application. And if we continue down this path and look through these JavaScript files, especially the one called main, that is actually the whole of the P2 recovery update tool. And that runs the binaries or the commands that we've seen when we were serially connected to the Minut. So we're going to see here, download firmware files, and here at flash files, it's going to tell you that it's going to run something called secflash. Remember secflash? That's an application that we found while connected by a serial. So now we know how to actually perform these upgrades. By continuing to analyze this file, it's possible to deduce the actual firmware download links. And I can finally download a P2SF file, which is a firmware file. Again, a Minut special format. You can see here it starts FS2P, so P2SF. And we can also see here immediately that here's Apple and here's boot. So we know we have the right file. Going through this file, I can see that some of the files that are mentioned are files that I already have extracted. And thankfully, this means I'm able to figure out this file format rather quickly, at least in a way that allows me to just extract the two files that I want. The Apple firmware and the boot firmware. And finally, I am now able to flash software to the device. So thanks to the RX command being available, it's really easy to transfer the files. We can check and see that there's now an apple.fw on the file system. And we now know that the command we need to use is secflash apple.firmware. And this will verify the file. You can see secflash, which is the command we need to now go and check the code for, verifies the firmware files. It erases the sectors. You can see 0802, that's where application lives. And once it's erased the sectors, it's programming the file, and then it comes back to us. So we're back into Ghidra, and we're going to go and find secflash. And we do the same as before. Here's secflash. We can see the usage. And thanks to that, we're going to find the method pretty quickly. We can see that Ghidra has not been able to figure this out. So let's make this into a function. This is apparently just the part that calls the secflash. We can see it actually takes the argc and argv. If parameters too few, it's gonna print the error message, and otherwise it's gonna go into the function. Let's figure out which one of these it is. Get our strings. And so we can see that this is an error message, and that's the one that flashes. All right. Here again, calling something. Let's see what that is. Okay, this looks promising. Let's go find the strings. Now, of course, not all binaries you will ever find are going to be this easy to decompile. Minut has, of course, since they have a menu with commands, they have these nice little printouts so that you're able to understand what you're doing. They also have a complete log system. We'll get back to how that works later. But that is definitely something that helps an attacker and not just the users. Now, the goal as an attacker here is, of course, to exploit this method. And we're going to call this, well, let's call it secflash because the other one was command secflash. There are indeed buffers going onto the stack. Some of them are quite large. That looks good. If we can get the secret stuff onto the stack, we're home. Unsupported cipher. That's interesting. So if local 28C is 0, UVAR is local 288. These GDOS decompiling is good, but it's not great. Quite often these will confuse the code. Now I'm lucky. I grew up on the 80s computers and I learned assembler language early on. I'm almost more fluent in the assembler code here than the decompiled C code, which is helpful when doing decompiling like this, because quite often this will fool you. If you go and try to find out the local 280C, the local 280H, which one of those is coming from what method, sometimes it's just better to go and check what are the registers that you're looking at instead. So we're going to claim that something here is probably going to talk about an unsupported cipher. Decryption failed. All right. That sounds like this is a decryption method. What we want to get to is an indication of what's the cryptography used here. At this moment, we don't know if Minut even knows how to do cryptography. I mean, they could just be faking it. And so we need to figure out what we have here. Let's go into the decryption method. A5, 63, 63, 66. These look pretty interesting. A5, 84. I wonder if there are any more like that. Let's see if these are some known magic values. So if we go and Google these, so throwing that magic value into Google, we will see that it comes up as AES. Big Endian tables values. This is a great way of finding out which encryption algorithm is used. And here comes an interesting comment. At this point, I pretty much know for certain that we're going to get into this device. And I think that will be a great place to stop this video. We just figured out that Minut uses in the secflash command the likely secflash key that we've seen before is 32 bytes. They're using AES, so this is AES 256. And I'm saying we now can break into the device. Either you know exactly what I'm talking about, at which point I think you're pretty much working the same things that I do, or you're now really confused as to how I claim that one of the most secure symmetric cipher algorithms that exist means that we have probably found a way in. So stay tuned for part 3, coming soon. Cheers.